So yeah, I still have a couple of exams left to grade from part two, but I'll get it done. Um, I guess sometime in the afternoon today. So yeah, because I still haven't had that part graded. I'll grade in a couple of hours. So today, yeah, we were going to continue talking about the determinant. So let me call that lecture 10. So what I was saying yesterday is that when you have two vectors, what colors was I using? Oh, when you have two vectors, AV and CD, the the determinant is just the area. I mean, once you have two vectors, you can make a parallelogram, like I'm doing here. And the determinant of the matrix that you get by putting these vectors as the columns of the matrix is just in absolute value, because if you remember, it can be positive or negative. So it's maybe better to think about it in its absolute value. In absolute value, it is a number that gives you the area of the parallelogram. Um, so yeah, so the only thing that I mean before talking a little bit more about this, it is useful to have an actual formula for the determinant, which I wrote last time, but I'm going to explain to you how you can figure it out. It's a nice thing to try just because it's like a nice application of like the properties of the rotation matrices. But before doing that, um, it's also useful to have another property of the determinant um, at hand. So this is like the rescaling property of the determinant. Okay, so let's think about it. Imagine you had, let me see, I want to, so let's say originally you have these two vectors, okay? If I make this way smaller, just for purposes of the picture. So let's say you have these two vectors originally. So boom, boom, boom. Here's like, you can make the parallelogram. So let's say this vector is AV, and this vector as always is CD. And now you rescale the vector. So let's call this area 1. So this is area 1. And then you rescale the vectors. So now let's say I'm going to make the pink vector 2 times bigger. So I'm going to multiply it by 2. So now it looks 2 times bigger. So now it's 2A, 2B, right? And let's say I'm going to multiply the blue vector by 3, for example. Let's see. I don't know how big it needs to look, but let's put it like this. So now it looks like 3C, 3D. Okay, and now you have a new parallelogram here, right? I needed a little bit more space for this to look like an actual parallelogram. Maybe I can just tilt it a little bit, make it more parallel looking. Okay, now it looks a little bit better. Okay, so the question is now, so again, I made the first vector 2 times bigger, and I'm making the second vector 3 times bigger, right? So the question is how what's the relationship between this new area, the area of the new parallelogram, and the area of the first one? Can anyone think about maybe what the relationship would be? Well, I mean, obviously it looks like A2 is larger, but by what amount? By what's the factor? Um, by what factor should A2 be larger than A1? Anyone guess? So one thing to do, you can do, if you wanted to, is, I mean, in this case, it's kind of very explicit, but you can do it. Like, you can literally put, like, make some copies of the first parallelogram into the second one. Like, for example, you could divide, like here, like this vector is twice as large, so there's like a copy of this vector that contains this one. So you can draw it here, right? So you are making 2 copies of these, right? And then you can split this other vector into 3 copies of the original vector. So 1, 2, 3. So you get something. Oops, let's change colors. So you get something like this. So right, well, you're thinking about it in terms of the formula of the determinant, which I still haven't given you. But yeah, the important thing here is that you're multiplying it by 6, right? So essentially, what's happening is that you kind of have 6 copies of A1 in here, right? Does that make sense? So even if you still don't have like the formula for the determinant, right? You can more or less pretty much tell that A2 should be 6 times A1, right? So A2 has to be 6 times A1. But what is 6? It's 2 times 3. That's a better way to see it. So let me put it as 2 times 3 times A1. Why am I writing it this way? Because if you notice, like the first factor was multiplied by 2. The first vector was multiplied by a factor of 2, and the second vector was multiplied by a factor of 3. So essentially, this is basically true regardless like of the numbers I had chosen. So whenever you rescale a vector by a certain amount and a second vector by another amount, the new determinant would just be the older determinant times the product of those rescalings. So let me put it like in this way. So what I'm saying is that, so like the property is, so the rescaling property is that if you take the first vector and you rescale it by some constant, I'm going to call this constant lambda. You could have called it a different thing, but let's go to lambda. So if I rescale the vector by a certain factor, which is what you see here. So in this example, lambda 1 was 2. And if I rescale the second vector by another factor, right? So you can put a CD. The determinant of these two matrix will be lambda 1, lambda 2, times the determinant of A, B, C, D. Is that making sense? So in other words, you can factor out like a constant, like just maybe an example just to make it more clear. Like let's put like something like pi, because maybe that's more easy to see, like what I'm about to do right now. What I'm saying is that, like, for example, if you so here's an example. If you rescale like the first vector by pi and the second vector by root of 2, what this is saying is that this is root of 2 pi times the determinant of 2, 4, 3, 6. Okay. So in other words, when you have like a constant or a number that appears in both factors of the determinant, then you can rescale it. I mean, you can take it out of the determinant. Okay, so I can take out the pi, and I can take out the root of 2. Is that making sense? So the constants can be pulled out of the determinant. In fact, you can still pull out some constants here. I don't know if you can see that. What can you take out here? Well, notice that, there's like a 2 that, yeah, it's kind of like a common factor. So let me take that 2 out. So let me take this 2 out. So it would be root of 2 times pi times 2, the determinant of 1, 2, 3, 6. Okay, so I'm specifying here what I'm pulling out. Okay, and in fact, even if you look at the second column, there's still something you can pull out, right? You can take out a 3 if you wanted to. So you can also say this is root of 2 times pi times 2 times 3, the determinant of 1, 2, 1, 2. Okay. Is that making sense? And then yes, it would be time sorry, yes, like a 6 root of 2 pi. Now this this determinant, we'll see, it ends up being 0, right? Because like the columns are, once you think about it this way, the thing that happens here, like for example, would be that you like the two vectors are the same, right? So like there's no, here you have 1, 2, and here you have 1, 2 again. So there's no area in this there's no area for that parallelogram. So the vectors are kind of parallel. They're the same vector. So that's why this area would end up being 0. But since there's no area here, but like what I'm trying to say is that ignoring that fact, maybe it was not so, it could have been clear, right? Kind of that maybe they kind of were like the same vector. I mean that the vectors were parallel, but it's less obvious here. But if you use the properties of the determinant, you get it to a point where like it's very explicit. Is that making sense? So that's kind of like how you. There are a couple more properties that I have to show you for the determinant, but this is one of the useful ones. But it's important to kind of notice that the constant that gets pulled out for each column, right? So you can pull out a constant per. I mean, when you fact pull out the constant is for each column. So the remark is that you pull out the constant for the pull out a constant for the column. So for example, sorry. Give me a second. Sorry about that. So in the case of if you happen to multiply let's say every entry of the matrix by 2, so imagine that you write something like lambda A, lambda B, lambda C, lambda D, right? What would that be? Well, there is a constant lambda that you can take here, right? So there's a constant lambda that you can, oh, it's taking some time to show. Okay. So if you have something like this, what's happening? You can pull out a lambda for the first column, but then you can also pull out a lambda for the second column. So it's one lambda per column. So it comes out as lambda squared. Okay. Again, it's taking a little bit of. I think it's taking a little bit of time to update on the video, but you see what's in happened. So it was not. It doesn't come out as lambda. It comes out as lambda squared. That's important to notice because again, it's one lambda per column, and there are two columns where you can take out the lambda. So it comes twice outside the matrix. Is that making sense? So just that's like a source of confusion many times that sometimes people will write like just lambda, but it has to be lambda. In the case of the 2 by 2 matrix, it would have to be lambda squared, okay? Because there are two columns that you can take it out from. Is that okay? Okay, so now let me just share again the iPad because I feel like this is like there's a small time gap between what I write on and what shows on the screen, at least when I see it. So let me see if if I share it again, that would make a difference. So with that remark, I can show you like the formula for. I can give you like the formula for the determinant of a 2 by 2 matrix, which again I mentioned before, but I haven't proved to you why it works the way it does. So let's talk about so let's just find the formula. Okay, now this looks a little bit faster. Yes. So again, I have this vector and I have this other vector. And I'm going to give you the formula for the determinant. The only thing that I'll do just to simplify my life, because like, I mean, it's just to illustrate the main ideas. So just as a simplification, I will assume that each vector has length 1. In the general case, there's not much that changes, thanks to this rescaling property. Because, like, say, if the vector didn't have length 1, like if the first vector has length 5, then you can kind of play with the rescaling properties and just multiply or divide by, depending on how you set it up. You multiply or divide by 5, so that like if the vector has length 5 and you divide by 5, you kind of shrunk the length to 1. So you see, like, if the vectors do not have length 1, you can just like rescale them so they have length 1. And that kind of like means that finding the formula in the general case is not that different from finding it in the case like both have length 1. It's just that it's a little bit easier because you have to keep track of less stuff, less variables. So it's better because of that. Okay. So let's see. It is a good argument. So just to set it up properly, here we have AB. Here we have CD. So what I'm going, like, well, I can still keep writing the copies of the other two vectors to have the parallelogram. What you can do is, for example, let's say that there was an angle theta, right? There's an angle theta between the first vector and the x-axis, okay? So let's say there's this angle theta, and let's say that there's an angle between the two vectors, okay? So theta is the angle between the first vector and the x-axis, and alpha is the angle between the two vectors, like the one that you see here in the picture. Okay, so here's a important question or remark. Let's say, what do you think happens? Like, do I have enough? Let me see if I have enough markers to do this, to pull this up. So I do. I don't know if you can see my, uh, here's one, here's another. I mean, I do, but it's confusing. It's complicated for my hands to put them all together. Let me see if I can. Um, okay. Well, it doesn't look quite perfect, but it's something like that. So you have like these four vectors making a parallelogram. It looks more like a square that I would like to, but okay. Think of it as a parallelogram. And here, let's say you have it this way, and let's say you start rotating it, right? So what do you have? What happens with the area of a parallelogram as you rotate the vectors? What do you think is happening? So try to think about it in this picture. You have this parallelogram, right? And you rotate, like, say, this vector and this vectors by a certain angle. What would happen with the area? So the area remains the same actually if you rotate the vectors by the same angle. So like what I'm going to do is the thing is like to find the formula for the area is kind of complicated because the sides are not aligned with the axis. So that's what makes it a little bit more complicated. But what I can do is just take advantage of the fact that I can rotate the parallelogram without changing its area. So if you do that, then you can rotate the parallelogram so the one of the sides, for example, is aligned with the x-axis. So that's what I'm going to do now. Let me see if I can put it here. So I'm going to rotate by what amount do I need to rotate if I want by what amount do I need to rotate if I want the pink vector to be along the x-axis? Well, there was an angle of theta here, right? So if you're, it's kind of like this question that we talked about before. How can you undo a rotation? Well, you can rotate this back to the x-axis just rotate it by an amount of theta, but clockwise, right? So you can rotate this clockwise by theta. Is that making sense? So if you rotate clockwise by theta, what happens with the pink vector? It gets aligned with the x-axis. And what happens with the blue vector? I mean, the blue vector gets rotated as well by some amount, so which is theta. So it just goes here. And now what's the angle between, like, what's this angle? What should I put here? What should this angle be? It's already in the picture from before. It's one of the angles from the picture from before. This is the angle between the blue and the pink vectors, right? So what should that angle be here? It should just be alpha because alpha it was the angle between these two vectors. And if you rotate them both by the same amount, the angle won't change between them. Is that making sense? Okay. And once you have something like that, again, this is like a regular parallelogram. So there, I don't know if you remember, there was a formula, hopefully that you saw maybe a long time ago for the area of a parallelogram. So the area of a parallelogram is base times height. Okay. The base is the pink vector, right? But it has length 1 because that was my assumption that I started with. I just, for convenience, I started with a vector that had length 1. So the base is just length 1. So I can put 1 here. And what's the height? Can anyone find the height in this picture using the information that you have here, like the angle and the... What is the height? Well, if you use trigonometric functions, the sine of alpha, right? What's the sine of alpha? Is h over hypotenuse. The hypotenuse is 1, right? So the sine of alpha is actually h. So the area is actually just the sine of alpha. Okay? It's just that now we have to um, think about it a little. That's fine, but leaving the answer in terms of the sine of alpha is a little bit weird because like alpha was not of the was not one of the original quantities that appear in the problem, right? Like the problem started with A, B, C, D, so there's no alpha there. So we have to just like rewrite this a little bit differently. But here's one way to do it. So this is the answer. I'm just saying that the answer is not too explicit. We want a little bit something a bit more explicit in this case. So what you can do in this case, like if you look at this formula, what this is saying is that the second entry um, is sine of alpha, right? Because the second entry of this vector is sine of alpha because that's just like the y coordinate. The y coordinate is this one. And what's the x coordinate? Well, the x coordinate has to do with the cosine, right? So this is cosine of alpha. Okay. So what? So this vector again. This is a vector that we obtained by rotating this vector. We took this vector and we rotated it by an amount theta. We rotated it by an amount theta clockwise to get to this one. So let me write that down explicitly. Cosine of theta, sorry, cosine of alpha, sine of alpha was obtained from CD by doing a rotation. By doing a rotation by an angle of theta. But we had, that's basically why at the beginning of the course we saw this rotation matrix. So what I'm saying is that what's happening here, if you prefer like a diagram, is that I started with CD. So what I'm saying is that I started with CD, I did a clockwise rotation. And I'm ending up with cosine of alpha, sine of alpha. So that means that this vector has to be the rotation matrix times this vector. I don't know if you remember the formula for the rotation matrix. It was this, it looks slightly different from the one we saw before, because before like there was a minus here and not here, but that's just because now I'm doing the clockwise rotation. So that's why there's like the change in the sign. But besides that, everything else is the same. Okay. So that means if you look at this formula, that if you do the matrix multiplication, that means the cos of alpha, sine of alpha is cos of theta times c plus sine of theta times d, and then minus sine of theta times c plus cosine of theta times z. So sine of alpha, which is what we wanted the sine of alpha, right? Because that's what appears in the area. So the area was sine of alpha, but sine of alpha is minus sine of theta c plus cosine of theta d. And that looks a little bit better because now c and d appear in this formula explicitly. So now we just have to replace sine of theta and cosine of theta. But that's easier because if you remember, we had this original picture. If you look at the original picture where this was called AB, I said that the angle between AB and the x-axis was theta. And I assumed again that this segment had length 1. So it's kind of the same thing. Like that means that if you look at the cosine of theta, the cosine of theta has to be adjacent over hypotenuse. So the cosine of theta is A. And if you look at the sine of theta, that's the opposite side divided by the hypotenuse. So that means that the cosine of theta in this formula, the cosine of theta is A, and the sine of theta is B. And in fact, I can change the color here to put them in blue. Okay, and that gives you the area being equal to minus sine, so it's minus BA plus cosine times D, but minus sine is B. Sorry, oops, so I did it, it's minus BC, I cut it wrong, sorry. Minus BC, and then the cosine is A, and there was D here. So that means that the determinant of AB CD if you look at this formula, is A times D minus B times C. And that's the formula that if you have seen this before, you are usually given, but this is one way to get it. And with that, then you can compute this once you have this formula, then you can compute the formula, you can compute the determinant quite easily. Okay, so this is an important formula for today. Yeah, I'm not, I guess, right. Yeah, I guess you could call this down phasing. I had not seen that phrase before, but yeah, I suppose it's all, like sometimes it's called the main diagonal. Oops, as well. But yeah, it's one diagonal. It's this diagonal minus a diagonal. It always goes that way. So let me do some examples. I mean, this formula is relatively easy. So if you do this, it's like 2 times 5 minus 3 times 4. So this is 10 minus 12. This is negative 2. So like, again, well, the fact that this was negative just means that first, like it means that in absolute value, that is the area. So the area is 2 of the parallelogram. The fact that it was negative just meant that, if you remember this from last time, that just means that you have to do like the orientation of the vectors is kind of like off, but it's not. I mean, the fact that it's negative is not something. It's fine. It's just not too much to think about it. It's just easier to think that in absolute value it gives you the area of the parallelogram. Or here's another one, like the determinant of like I mean, they're all like more or less look the same. So if you have this vector, it is 3 times 3 is 9. there's always a minus from the formula. That's something you have to be careful about. So it's minus 7. So it becomes 9 plus 7. So that's 16. Okay. But, like the formula is very easy to compute, in fact. So it's one diagonal, and it's always like the main diagonal first. So there's not really too much where, like, to get lost in. But so yeah. Is that okay? Is that making sense? There's another one. Okay, so now that you have these formulas, you can start proving certain things. So another thing that's useful you can do with this one is determinant of a transpose. So I don't think I had told you explicitly what the transpose of a matrix is, but I can tell you now what it is because it's a very simple definition. So what is a transpose of a matrix? So this is called A transpose or AT. This means A transpose. So it is a matrix whose columns are the rows of A. That's it. So for example, if A is like 1, 2, 3, 4, what is A transpose? So the columns are the rows of A. So this is the first row. Now it becomes the first column. And this is the second row. Now it becomes the second column. So it's essentially the transpose is just changing your mind about what's a column and what's a row, right? So that it's kind of like turning the rows like vertically into columns, and that takes off everything. Okay. Or if A is like, you can do it even in the non-square case. So like 1 minus 1, 0, 2, 3, 5. Then A transpose is like, again, you just make the rows vertical. So 1 minus 1, 0, 2, 3, 5. So in general, if A is m by m, right? Like A transpose basically changes since it's changing rows with columns, it changes the order, the size of the matrix. So A transpose is n by n. Is that okay? For now, this transpose, there's not too much. It's kind of like a natural thing you could do, I suppose, but it's not that we're doing too much with it at the moment. But it's kind of useful to at least bring it up. But later on, the transpose will become a lot more important. But for now, it's just like, oh, there's this thing called the transpose, and that's how it works in practice. But at least you can compare the determinant of A with the determinant of A transpose. So let's just think about it. So let's say, let me put it in color. So let's say A had been A, B, C, D. What would be the determinant of A in this case? Is A times D minus C times B, or right? It's still this diagonal minus this diagonal. But then what's A transpose? Again, it's just changing your mind about the rows and the columns. So the transpose becomes A C B D. But if you look at it, like, okay, yeah, but the answers are different, but kind of like for the product that we care about, the determinant is essentially the same, right? It's AD minus BC, but it doesn't matter, this and this is the same because they're numbers. So you end up concluding that the determinant of A equals the determinant of A transpose, which is actually kind of like useful again. And this is like the property that will continue being true in general, not just for 2x2 matrices. I still have to give you like the formula in the 3x3 case, but it's not so clear, it is a property that holds in general, but it's not so clear, like geometrically, why it would be true, because you're changing they're literally different vectors, right? So if you think about this as a vectors, now you're comparing the area of this parallelogram with the area of this parallelogram. So the vectors do have different entries, so it's not so obvious whether like areas would be the same. But here is one case where, like, if you actually look at the formula, it just becomes clear that they had to have the same area, even though it may not be so clear from like the geometric picture why it had to be true. Right? It's more easy to see it in this case from the formula. Is that okay? Okay. So let me give you just one more formula for the 2x2 case, and then after that we'll move on to the general case. So this is actually the most important reason for why the determinant is useful. So I haven't really said why the determinant is useful, but now this will explain why why is the determinant a useful quantity? Like and it is because of the following formula. So the great thing about the determinant is that there's like a formula for the determinant of the product of two matrices. Okay, which is very simple. You'll see in a second what that is. But so if you multiply two matrices and you take their determinant, there is like a very simple formula for that. So let's try to think about what that formula should be. So let me remind you first how you could think about the determinant in a more pictorial way. So if you had like let me see if I need to zoom in, sorry about that, just because otherwise the pictures won't have enough space. So let me zoom in. Okay. So if you remember, one way to think about the determinant is that you have the unit vectors E1 and E2 and E2. That gave you the unit square. Okay, so that's what we did last time. And here's again the way you should think about the determinant, or sorry, a matrix. This is an important idea. If you have a matrix, A, what you should think is when you multiply. Let me put this. Okay. If you have a matrix A, well, you can multiply each of these vectors by A, right? We know we can do that. You get two new vectors. And so what happens in general is that when you do the multiplication, the square, right, this unit square you began with just literally turns into some parallelogram, right? So when you do the matrix multiplication, where you're multiplying each side by A, right? This you get a parallelogram here. Maybe it's a bit longer, so let me put it like A E1, and then you get a second vector here. Maybe this one becomes shorter. I don't know. So you can put here A E2. But what I'm saying is that when you multiply each of these vectors individually by A, you get a new vector, right? So in general, they will remain perpendicular, the new vectors, and they may change, their lengths may be different compared to the original length. But the point is that no matter that, regardless of that, like you get a new parallelogram, right? And this new parallelogram has area, right? So this one has area 1. I'm assuming here that everything is with positive number, that all the determinants are positive, so that like the picture is completely accurate. But that's fine. I mean, it is true in this picture. So the area of this parallelogram is determinant of A. Okay, and now here comes the cool thing. You can now, you kind of you can do this again, but with the second matrix B, right? So what you can do this again is like you can, for example, multiply this vector by B. Okay, so when you do that, you can put it here. Right, so I'm multiplying this vector by B, so that's why I end up with BA E1. And then you can multiply this vector by B, and I don't know where it would land. Let's just, I mean, again, I'm trying to just make kind of like a picture that's easy to draw. So let's just put it here. So you get a new parallelogram. And what's the area of this new parallelogram? Well, if you think about it, if you start from the original picture, right? You know, to get from here to here, what you're doing is a matrix AB. Okay. So the area of this last parallelogram is a determinant of BA. Okay. So that's what's going on. And I'm going to give you a formula for this area. You'll see in terms of the determinant of A and the determinant of B. But is the picture clear? So you start with the unit square, okay? You start with the unit square. When you multiply each side of the unit square by A, you get a new parallelogram. And when you multiply each of these sides by B, you get a new parallelogram. So we have to we ended up with a third parallelogram. And the thing is just that you know, you can think about it as a single step, as a single process where you go from the original square to this one, like using the product matrix. That's like the idea of the product multiplication. Essentially, that's the point of a multiplying matrix, is that it really represents two matrices, like like, you know, concatenation of two processes. Okay. So let me just focus. So like just to show you how this works, let me focus on the last two pictures. So let's just focus on this to show you what the formula should be. Let me focus on these two pictures. So I'm going to redraw them by just exaggerate a little bit the pictures to make them more clear. So what's happening here is that I'm going to I'm going to use an idea that's very common if you have ever taken calculus. So what I'm going to imagine is like I have this parallelogram and I'm going to chop it up into mini squares, which you see here. So here, these are squares. So I'm using like mini squares of area, uh, of like area like epsilon square. So imagine each square is so small, it just has sides of like the sides are just of length epsilon and epsilon. So usually, like again, it's kind of like a common idea from calculus. When you think of something being really, really small, you just call it epsilon. Okay, and so what's the thing here? Well, of course, like this is a parallelogram, so you know when you try to cover it with squares, as you try to cover it with squares, you may not be able to cover every part. You know, there would be some corners or some regions of the parallelogram where if you try to cover it with the square, you would have to you cannot really do that because the parallelogram is kind of tilted and the squares are all parallel to the x-axis, right? But the idea is like the more squares that you use, the smaller that they are. Like the stuff that you are not able to cover of the parallelogram with squares gets smaller and smaller. So if you use really really small squares, you will more or less be able to cover almost all of the parallelogram. And the smaller the squares you use, the better and better this gets. So when they are really small, when they're really small, or the smaller they get, like let me put it this way: the smaller their area, the better they will cover the parallelogram. So how many are you going to need? How many squares will you need for that? Well, roughly you will need. I mean, remember again, this had area equal to the determinant of A. I had already said that before. So like just to make it easy, like imagine that like the area had been 10 and each square has like area 0.5. So that means that roughly you need 20 of them to cover the entire parallelogram. So essentially you roughly you need area like the area divided by epsilon square rectangle squares. So the number of squares needed is roughly the determinant of A divided by epsilon square. Okay, so that's like kind of the number of squares that we need on this side. Okay, again, this may not be so clear right now when I'm doing it, but for now I'm just saying like if you have a parallelogram, you can imagine just chopping it off with tiny squares. I'm trying to cover the parallelogram with that. Okay, and how many squares like that you would need? You would need basically this number. So why am I doing this? Because let's go to the second picture. So again, I'm focusing on these two last parallelograms here. So to go to the last parallelogram, to the third one, in this picture, we had to use the matrix B. So what happens now is that this new parallelogram had area, right? The area of the new parallelogram was determinant of B times A. But if you look at this, let's just keep track of what happens with an individual square. So what happens with an individual square is that, like, it kind of gets distorted. If you had like a square here, you kind of it gets distorted, and it becomes like a small parallelogram. So one of these squares, let me just keep track of it, becomes something like this, right? Because again, like the idea is that the matrix, when you use like the matrix B, the point of a matrix is that it distorts and turns a square into a parallelogram. That's what you saw here. So it's kind of like the same happens for these mini squares. So each of these mini squares kind of becomes a parallelogram. So now the squares become a parallelogram of what area? Of area. Well, essentially the area is epsilon squared because that was the original area of the square. But the distortion factor is the determinant of the matrix that they are using. So again, from going from here to here, that is, you multiply by the determinant because you started with something of area 1. So the distortion, the determinant was just at the area. But here, because the area is epsilon squared, like the new area is just epsilon squared times the determinant of B. Okay? So each of these ones has area epsilon squared determinant of B. Okay, but the point is that if you had 100 mini squares here, then you just get 100 mini parallelograms here. But the number of parallelograms is kind of preserved. You're using the same number. It's not that you created or destroyed the squares. So the numbers are the same. The numbers of squares parallelograms remains the same. It's kind of like a conservation law for squares. They cannot be destroyed when you multiply them. But now how would you compute this number on this side? Oh, this number would be the total area divided by the area of each parallelogram. So it would be the total area, which is the determinant of V times A, divided by the area of each mini parallelogram that covers it up. So each mini parallelogram has area S epsilon squared determinant of B. And since these two numbers are the same, right there, the same n, you get that the determinant of A over epsilon squared equals the determinant of V times A over epsilon squared determinant of B. And I don't know if anyone can solve this equation, right? Like you can cancel the epsilon squares. And so you get one of the most important formulas of like the determinant, or probably the most important formula of the determinant, which is that the determinant of B times the determinant of A is the same as the determinant of B times A. In other words, to do the determinant of a product, the determinant of a product is just a product of the determinants. Okay. And again, this is really, 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 really useful. Uh, if you didn't have this property, the determinant would not be that important. Why is this? Um, why is this formula useful? So why is this useful? Well, let's think about the matrices that had an inverse. If you remember a matrix that had an inverse, what was the property of the inverse of a matrix? It was that A inverse times A equals the identity matrix, right? Right. A matrix had an inverse if there was another matrix with the property that A inverse times A was the identity, right? So that if you take the determinant of both sides of this equation, because I mean that's something you can do. It's kind of like taking the square root of both sides of the equation. You can take a determinant of both sides of the equation. Um, you get this. Here, like the identity was 1001, right? But what if, okay, what is it? Let's start with the easy part. What's the determinant of the identity? The determinant of the identity is 1, right? And what's the determinant of these? Well, it is the product of the determinants, right? Is that making sense? So what this is saying is that the determinant of, if A has an inverse, the determinant of A cannot be 0 because if the determinant were 0, it's impossible to satisfy this equation. So in other words, if A has an inverse, determinant of A must be non-zero. Otherwise, like this equation would not be able to solve. And moreover, the determinant of A, the inverse is one of the determinant of A. Right? If you can solve this equation for determinant of A inverse. So that gives you like a very, so before, for the first exam, if we wanted to know like if a matrix had an inverse, we either had to like kind of we had to try to find explicitly like the inverse, right? Here it's kind of like a check to see whether you're wasting your time or not, because if there's no point in like in trying to find the inverse of a matrix with determinant 0. So let me write it in a word that in a way that is more useful. So if determinant of A equals 0, A cannot be inverted. A has no inverse. A inverse does not exist. That's the easiest way to say this. And that's like the fastest way. I mean, that's kind of the easiest way, at least, to know whether A inverse exists or not. If like, or whether you're wasting your time uh, trying to find an inverse for the matrix. So, for example, this determinant is 6 minus 6, which is 0. So this matrix has no inverse, and that's it. There's nothing else that needs to be checked. And so in the 2x2 case, like, I mean, the 2x2 case was relatively easy. But that's like another reason, like, I think some of you have seen this formula before, because definitely some used it during the exam, but like there's a formula for the inverse of a 2x2 matrix, which some of you may have seen from this is also explains why that the inverse of A, B, C, D is 1 over the determinant of A times dA minus C minus B. So there's this easy formula for the determinant of a 2x2 matrix. And so if you look at this formula, it requires dividing by the determinant. So that kind of is telling you the determinant could not be 0 to begin with. Is that making sense? So let me give you, okay. So that's more or less everything that I wanted to say about the 2x2 case. I tried to do everything super explicit in the 2x2 case so that you would see how the formulas are supposed to work. But let's take a 5-minute break, and when we come back, I'll tell you how the general case works. But for the general case, I won't try to go over all the proofs. I will just more or less tell you how it works. The many proofs are very similar to what we just did. It takes more patience because the matrices are bigger. But I'll tell you the basic important facts. So let's talk about them let's take a 5-minute break and then we'll talk about it. Okay, so I'm going to tell you more about the now I'm going to tell you about the determinant in the general case of an n by n matrix. So they're always only defined for square matrices. So um, so first, like just to give you an idea, like in the 3x3 case, what's going on in the 3x3 case? So you have a matrix A, which you could write like A, B, C, D, E, F, G, H, I. And so that means that there are 3 vectors, right, in this picture. It's always hard to see to check what I should draw first. So okay, yeah. I don't know if it's clear what I'm trying to do here. I'm trying to draw like some sort of box, or sometimes it has like what is it called, parallelepiped or something like that. But the point is that once you have 3 vectors, you can draw like a box. So this is vector 1, which is column 1. Column 2 is here. Oops. And column 3 is here. So there's some box. There's some box or parallelepiped. And so the determinant is going to be a number. It's a number with the property that in absolute value, the absolute value of the determinant is the volume. Now it's no longer area, but volume. Is the volume of this box. Whose sides are C1, C2, C3. And in general, for an n by n matrix, the determinant is kind of like a hypervolume. It's not something that you can anymore visualize, but it works the same way. So in the general case, and and for the n by n matrix, the determinant that A is a number such that in absolute value, it gives you some sort of hypervolume or of the hyperbox. I mean, you don't have like a good way to describe it, so you just put like the phrase hyper in front of it. Uh, this is why if you have taken multivariable calculus before, there's like a change of variable formula in multivariable calculus. I don't know if anyone has taken it yet. But there you'll see that there's like a thing called the Jacobian, and in the Jacobian is like a determinant. And the reason is for this, because the determinant is like some sort of area or volume. So this is related to the change of um, variables formula in multivariable. Okay. But so let me give you so what I'm saying is that the determinant, regardless of the size of the square matrix, is some sort of like area or volume or hypervolume. So it's something like kind of giving you something geometric about the vectors that make up the matrix. So many of the properties, again, have similar proofs. Some are a little bit harder, but the properties that I was stating for the 2x2 case continue to work. So let me give you like the main properties in the general n by n case. So there are a couple. First, yeah, where should I start this? Let's start with the most like important ones that like the end up being convenient. Like why the determinant is useful. So the first one is that is you still have some like this property that the determinant of a product is the product of the determinants. So I mean, this is also I mean, I didn't say it last before, but since this is just like a product of two numbers, it doesn't matter in which order you put them. So actually, this secretly is saying that the determinant of B times A is the same as the determinant of A times B, which is kind of interesting because remember, like the four matrices, the order does matter, but once you take the determinant of the matrices, like the order of the multiplication stops making a difference. So it's kind of like a fun thing as well to have. It's still true that the determinant of A equals the determinant of A transpose. It's also true that if the determinant of A is 0, then the matrix has no inverse. That's one of, I mean, that continues to be true because of this thing. So if determinant of A equals 0, A has no inverse. What's also true, and I didn't explain, but is the converse. So if the determinant of A is not 0, and then A has an inverse, which is not clear from what I have said. But if the determinant of A is not 0, A inverse exists, and you have a formula for the determinant of the A inverse. So the determinant is essentially what tells you whether you should waste your time trying to find an inverse. If it's 0, don't even bother. If it's non-zero, try to find the inverse, and you will know even like the formula for the determinant of the inverse. So like, so what I'm saying is that this is for our purposes, this is perhaps the most important property of the determinant. That it is like the best detection tool for invertibility. Okay. And this is also related to the inverse property. But if the determinant of A is is 0, that means that the columns are linearly dependent. The columns which make up the matrix are linearly dependent. And the determinant of A is non-zero. The columns are linearly independent. Okay. So these are for like the main properties of the determinant. There are a couple more properties, but like the ones that everyone should really memorize. The key properties are these. Okay. These are really what gives the determinant like its power, like in terms of properties. Everything else is kind of secondary. The fact that it is used to determine invertibility is one of the biggest factors in everything. Okay. So the thing that at least I'll finish by telling you today is how do you find the determinant, like an explicit formula for finding the determinant of an n by n matrix. So let's try to talk about that. So it's better to explain it with an example. Let me start with the case 3x3 case. So the cool thing about this formula is it's kind of self-referential. So the formula for the 4x4 case depends on knowing the formula for in the 3x3 case, and the formula in the 3x3 case depends on knowing the formula in the 2x2 case, and so on. So it's kind of like this Russian dolls that one is inside the other. Like it kind of depends on the previous one. So before saying like the formula in that case for 4x4 case, anyways, I would need to go through the 3x3 case. So let me give you the formula for the 3x3 case. So what you do is like you have again you have this matrix A B C D E F G H I, and to the matrix you associate like a matrix of signs. It always starts with a plus and then it just alternates. So it's plus minus plus plus minus plus minus plus minus plus minus plus. So this matrix of signs always begins as a plus in the upper left corner, and that kind of settles determines everything else because it has the sign has to flip. Okay. So for example, the idea of like the determinant to compute it in the 3x3 case is that let me give you the formula. So like the nice thing about the determinant here is that you can choose like your favorite, like say let's choose like our favorite row. You see in a moment that doesn't matter, but let's choose like our favorite row. So I'll choose like row 1. Okay. So what I'm going to do is like the idea is that again it's kind of this is one of those formulas that is easier to explain in person. But what I'm going to do is you kind of pick up the coefficients that appear in the first row or the numbers that appear in the first row, and you just put them in order with the sign that corresponds here. So A appears as plus A, D appears as minus D, and G appears as plus G. Okay. So this plus minus plus just comes because in the first row, the table, the matrix of signs is plus minus plus. Okay. So you do that, and then let me see. I may need some more space. So let me. And then the rest is very easy. What you will do is kind of eliminate, like, so for A, right? Where does A belong? A belongs to the first row, first column, right? So what you do is kind of eliminate the row and column to which A belongs. So when you eliminate the row and column to which A belongs, you see a 2x2 matrix, which is this one, right? And so you take the determinant of that and multiply the answer. So I'll multiply the answer of A times the determinant of E, H, F, I. Okay. Then let's go to the second term. It's D. So with D, I have to eliminate the first row and the second column. So I don't know if you see like that there are like 4 numbers left, which are these two. So I will put here B, C, H, I. And for the last one, I have to eliminate the row and column to which G belongs. Oops. So the row and column to which G belongs is this one. And so you get this matrix, B, C, E, F. Okay, so it's basically the idea is that you kind of extract the coefficients with the corresponding signs, and then you multiply each coefficient by the determinant of the 2x2 matrix that you get by deleting the row and column to which they belong. So for each coefficient, you remove the row and column to which it belongs and compute the determinant of that. So let me do it in an example because just easier to see in practice. So let me do an example here. Let's say the matrix has been like 1, 2, 0, 9, 0, 2, 2, 4, 5. So again, the matrix of signs is plus, minus, plus, minus, plus, minus, plus, minus, plus. So the matrix of signs again always starts with the plus here. And so if you want to use let's say I wanted to use the first row to find the determinant. Okay, so I focus on this stuff. So the determinant along the first row is plus 1 minus 2 plus 0. So plus 1 minus 2 plus 0. And then you just have to figure out which 2x2 matrices to put here. So what do we put here? You have to put the matrix that you get by deleting the row and column to which one belongs. So it's 0, 2, 4, 5. So then for another one, you delete column and row to which 2 belongs. You get 9, 2, 2, 5. For the last one, I mean, the last one obviously doesn't matter too much because there's a 0 in front of it, but I will still just write it so that you can see what it gives you. It's 9024. Is that making sense? Are there any questions of how I'm choosing? Like, the important thing is to just understand how you're choosing the matrices. Once you do that, everything else will be easy to compute. So is that okay? Are there any questions about this? So the middle rule. So let me see if I understand the question. Can be 2, 5. You mean like when you say middle row, you're saying like doing this, oh, let's see. If you do the third column, then the first column, for -2. So let's see. Oh, okay. I see, I see. Oh, right. Like if you, okay, I get you. I'll mention these properties of the determinant. There is a property that says that you can swap the columns and you change the sign. So I don't know if that's what you're referring to, but yeah, you could swap these columns and that would change the sign of the determinant. So it would become +2. Although in practice, for something as small as this, it doesn't make too much of a difference. But yeah, it's an option if you wanted to see it as positive. Yeah, if you didn't want to see a minus here, you could do the swapping of the columns. But I don't think you gain too much. You At some point either have to remember swapping the columns or like putting like the minus. So I don't know, like which one is worse. But if you do it this way, it's kind of like always the same like procedure. So that's why I'll keep it that way. But yeah, there are there's still a couple properties left about the determinant that I'll mention tomorrow. So one will be that one. So, but then each determinant is like the point. The nice thing here is that each determinant is easy to find. So this gives you, remember, this diagonal gives you 0, and this other diagonal gives you 8. So it's 0 minus 8. Then this diagonal gives you what, 45, right? And this diagonal gives you 4. And I mean, I don't care what this one gives you because there's a 0 in front of it. So like, let's just put +0. Who cares? So it gives you -8 plus, this is what, 41? And so it's 41 minus 2, right? So 41 times 2 is 82, right? So this gives you -90. Is that okay? The nice thing is that you don't have to choose the first row. So there's nothing about the first row that's special for computing the determinant. You can actually choose any row or column that you like. So let me do it again with a different row or column. So remark, you can do the same with any row or column. So for example, let me repeat the matrix. Like the matrix was 1, 2, 0, 9, 0, 2, 2, 4, 5, right? So before I chose the first row, like now, for example, you could choose the second column. I'm going to choose the second column because there's at least a 0 there. And as you may have seen, like having zeros is useful because like it avoids computing at least a determinant. So I'm going to still write the matrix of signs, but now I'm going to do it using the second column. Okay. So now the determinant of A using the second column, what's it going to be? It's going to be, now remember, it's with the corresponding sign. So it's -2. And let me put it here. It would be -2, right? +0, although that doesn't matter too much. And then -4. Okay. And then what you do, you put the determinants of the 2x2 mini matrices that you get. So when you delete the 2, right, you get 9, 2, 2, 5, right? When you delete the 0, let's delete the 0. What happens when you delete 0? You get 1, 0, 2, 5. And when you delete the 4, what do you get when you delete the 4? You get 1, 0, 9, 2. Is that making sense? Is that clear how I'm getting the mini matrices? If you understand that, then you're basically are good to go because every problem about computing determinants more or less is the same. You just have to do this a couple of times. So it's always, you just always delete the row and column to which the coefficient belongs, and then you can compute the determinant of what you get left. So it's -2. Again, this is 9 times 5 is 45. -4 plus 0. I don't care about that one. And then -4, 2, -0, right? So you get what? This is again 41. So 41 times -2 is -82, right? And then this is -8. And then this gives you -90 or -90. So it's the same as before, right? Which should be what happens. Like you shouldn't get like the answer shouldn't depend on which row or column you choose. So another, if you want to, I mean, we're kind of more or less out of time now, but if you want to keep practicing this, like just choose a different row. Choose for example a more complicated row if you want. Choose the third row and check that even if you choose the third row, you get -90. Okay. Of course, in practice, you should never choose a row without any zeros. Like if there's like something with zeros, you have to kind of prioritize choosing the one with the row or column with most zeros. So in this case, the most that I could choose was like 1 0. But if there had been like a row with 2 zeros, then go for that one. You see? So that's kind of how this works in general. Is that making sense? Okay, so yeah, this is what I guess what I wanted to say for today. So tomorrow I'll just we'll finish telling you a couple more things about the determinant, and then we may start with a new topic about vector spaces. But yeah, so for today, this is all that I wanted to say. I'll see you tomorrow.